Hi there, MG5004 or DE5418. This is topic 11, class 1. And what we're doing now is you've learned all the actual skills of integration. You've learned all the techniques that we need to know for the course. Now we're just going to use them in different ways that are applicable to engineering. Should we just review this idea that the area under a curve is given by the integral, provided, and this is a big proviso, provided all of the area is above the x-axis. So this is a fundamental theorem of calculus, and it works. You can find the area between B and A underneath the curve, so this area in here, just by simply finding the area between A and B, the integral of the function. Now it only works if the area is all above the x-axis, which means unless you know for certain that it's all above the x-axis, then you're going to get your answer wrong. Let's have a look at an example. As an example of the fundamental theorem of calculus, let's just assume that we know what we're doing, so that the area is the integral between 1 and 3 of the function, and the function is x squared minus 6x plus 5 with respect to x. So we do the integration, so it'll be x cubed over 3 minus 6x squared over 2 plus 5x. And remember, I don't mind if you put c in there and subtract it later, I just tend not to. And we do all the arithmetic, and that would be 9 minus 27 plus 15 minus a third minus 3 plus 5. Now this is where you see it's really weird, because that's what our answer looks like. Now clearly that can't be right. You cannot have the area as being a negative number. And while you might be tempted to just go, oh, well, I'll just take the positive of that, you do need to be careful about what you're doing. When you're finding an area using integration, you really need to do a sketch. So let's just do a quick sketch of this one. It's going to cut the y-axis at 5. If we factorize that, that would be x minus... what would it be? It would be x minus 1, x minus 5, just check that, that's x squared, minus 5x minus 6, so minus 6x plus 5, yes, so that's the curve, so it's going to cut through at 1 and 5. And you're asked to find the area bounded by the curve and the x-axis and x equals 1 and x equals 3. So now looking at it, all of the area is underneath the curve. So for bits that are underneath the curve, we need to take the absolute value of it. So in this case, the area is the absolute value of the integral. And so in this case, it will just be the absolute value of negative 5 and a third. So that was the sort of finding the area question that you would have done if you'd done the diploma course or from school. But what we have to do now is we have to go a bit further, and we have to look at finding the area bound by a curve where the curve is expressed parametrically. So let's look at the first one here. I may get space to do both numbers 1 and 2, but I'll certainly, for number 3, I'll do that one in class. Now let's have a look at number 1. We know that the area is going to be the integral between the limits of the function. And in this particular case, we're given the limits as, we're given the limits as 2 and 1, and we need to find the function. Now, if we write it out in baby steps, let's just leave it as beta and alpha for the moment. Now, we know that y for this first question is given to us as 2at, but we actually need to find dx as well. So we're told that x is equal to at squared, so dx by dt is going to be 2at, so dx must then be 2at dt. So we can put all of that into here. So now we've got, it's the limits. Now we're now talking in terms of t, and our parameters were in terms of t. So in this stage, this step here, it's not correct to put the 2 and the 1 there, because we've still got with respect to x. But now everything's in terms of t, so now we're fine to put in 2 and 1. And so we've got 2at. Now dx is now also 2at dt. So what we're looking at is finding the integral between 1 and 2 of 4 a squared, t squared dt. So 4 and a, or a squared, are constant, so we can put them outside. Then we can do the integration. The integral of t squared is t cubed over 3, and now we can put in the limits of 2 and 1, and that'll give us 28 a squared over 3. Okay, I do have space to do number 2. Now, the method is always the same. Express x and y in terms of the parameter, then we have to change the variables, and then we have to insert the correct limits of the parameter. So we'd start off by saying a is equal to the integral between alpha and beta of y dx. So we're going to put in what y is for the second question, and y is, you're told that it's b cos theta, and that's still going to be dx at this stage, but do it over here. But x is equal to, what's x equal to? X is equal to a sine theta, so dx by d theta is going to be a cos theta, so dx is going to be a cos theta d theta. Now we can put that instead of dx. So now we've got b cos theta a cos theta d theta, and everything now is in terms of theta, so we're fine to put the parameters in which are in terms of theta. Now a and b are constant, so we can take them out and do the integration between 0 and pi of cos theta times cos theta, which is cos squared theta. And we've done that before, so I won't do it here. So it's going to be AB times now be theta over 2 plus sine 2 theta over 4, or I could take the half out, whatever, it doesn't matter. And if we do the arithmetic at that stage, then we get AB times pi over 2. if you're a bit puzzled about the integration, just remember that cos squared theta is equal to 1/2 times 1 plus cos 2 theta. And that's what enabled us to do the integration as it is. So I will do number 3 in class. We now need to turn our thoughts to finding the mean value of a function, and we can do this by integration as well. If you have a look at the diagram, the graph on the left, it shows a rectangle whose area is clearly less than the area under the curve between 2 and 5. The rectangle has a height that's equal to the lowest point on the curve. So here, so its height is that, and clearly that's going to give us an area that's too little. The middle graph shows a rectangle whose height is equal to the highest point between 2 and 5, and clearly that's too big. So I guess by now you're thinking, well, isn't there a rectangle that's taller than the short one and shorter than the tall one, whose area is the same as the area under the curve? Well, of course. And this rectangle obviously crosses the curve somewhere in the interval between 2 and 5. This is the so-called mean value rectangle, which is shown on the right. And it basically sums up the mean value theorem for integrals. It's basically just common sense. But here's the thinking behind the maths mumbo jumbo, if you like. The area is the integral between a and b of the function like that. Now we know that. Now if we're looking at the third diagram here, the height of the rectangle is going to be whatever value f of c is, times the distance between, we'll just call it a and b, like that. And f of c is the average value of f of x. So these two things are true. So to find f of c, what we must be doing is we must be dividing the area by b minus c, which also means that we must be dividing the integral by, whoops, that's b over a, by b minus a, or conversely we are multiplying it by 1 over b minus a. So that's where this formula comes about. So it gives us the height of the rectangle, which is the average value of f of x. Another way to look at it is to say, well, it's the area over the distance on the base, or the mean value is 1 over b minus a times the integral of y between a and b. Let's check out some examples on the next slide. For question 1, we'll just use the rule that the mean is equal to 1 over b minus a times the integral between a and b of the function. And so we can do that straight away. So that's 1 over 2 minus 1, be careful there, of the integral between -1 and 2 of the function, which is 3x squared plus 4x plus 1 with respect to x. 1 over 2 minus 1 is 1 over 3 times the integral. The integral of 3x squared is x cubed plus the integral of x squared of x, sorry, would be x squared over 2 times 4, so that would be 2x squared, and the integral of 1 would be x. We're going to find that between 2 and -1. So that's going to be a third of 8 plus 8 plus 2 minus -1 plus 2 minus 1, which would give us a third of 18, which is 6. Now, it's not an area, it's a value. So if the function was volts, then the mean value would be 6 volts. In this case, it's just a random function, so the mean value is 6. Let's have a look at the second one. The mean this time is going to be 1 over pi minus 0 times the integral between 0 and pi of 3 sine 5t plus 2 cos 3t with respect to t, and that's 1 over pi. Now doing the integration, we negative 3 over 5 cos 5t plus 2 over 3 sine 3t between pi and 0. And if we do the arithmetic there, we would have, excuse me, 1 over pi times 6, which is, 6 over 5. So it would be 6 over 5 pi. And again, it's not an area, so it's just 6 over 5 pi. It's an average number, it's an average value of the function. That function, that's y equal to 3 sine 5t plus 2 cos 3t. Let's think about the mean value. If we were looking for the mean value of a sine curve where it's cyclic, and this bit's positive and this bit's negative, if we were to take the average over the whole cycle, then the average value would be 0, which kind of really doesn't make sense. So what we do is we use a statistical technique here where we take the squares, which means we're changing the negative bits into positive bits, and then we take the square root of all of that, the sum of all of that. So what we're doing is we're finding something that instead of being the mean, we call it the root mean square, and it's the square root of the mean value of y squared all the way between a and b. And to find the mean value of y squared, we use the integral. So this is how we get the formula here, that it's the square root of the mean value, but not the mean value of y, the mean value of y squared between a and b. So it's a statistical technique, and it gives us something that's more useful. It's useful. It's not limited to being useful to the electrical people, but particularly useful. It's looking at effective currents, etc. It's useful for when we're looking at gyroscopes, where you might be looking at the root mean of moments about an axis, for example. So basically anything where you've got a cyclic thing going on, it's useful to look at what we call the root mean square. Now, I will do this problem on the next slide because it's going to take more room than I've got here. Right, the question is asking us to find the root mean square of a function that is clearly cyclic. It's a sine curve. Now, it's often a very good idea to do a quick sketch of whatever it is you're talking about. and the amplitude, if you remember back, is going to be 400. And it'll be a sine curve. It's not a shifted one. Now we need to find the time period. The time period, remember from the formula, is 2 pi over omega, and in this case it's 2 pi over 200 pi. So the time period is 1/100th of a second. Now that's interesting, and we'll have a look at that more in a minute. So this number here is 1/100th of a second. Now we don't need to worry about anything else at the moment, just the fact that it's going around once, and we're finding the root mean square for the function over the whole of its period. So the root mean square, just using the formula, would be 1 over 100 minus 0 times the integral between 0 and 1 over 100 of the function squared and now we can make it a bit simpler for ourselves. We can square the 400 and take it out because it's a number, so it's not going to be integrated, so we can put that out. So that's, what's that, 16 and 4 noughts, and that's over 1 over 100. Now we've got to integrate between 0 and 100th of sine 200 pi t squared. Okay, you remember how to do this? This is from quite a way back. What we need to do is we need to change it into using a trigonometrical identity. So we're going to change it into this form. Got the coughs there. Right. Okay, so we can take the half out as well and deal with the over 100th. And so we've now got 8 and 1, 2, 3, 4, 5, 6 zeros. And so we've taken the half out, we've dealt with the 100th, and now we've got the integral of 1, which is t, minus the integral of, that becomes 400 pi t, so it would be sine 400 pi t over 400 pi, and you would do that between 1 over 100 and 0. Okay, putting in the numbers then, that would be 8, 1, 2, 3, 4, 5, 6 times 1 over 100 minus 0 minus 0, which is going to give us the square root of just 8 over 100. Now, here's where we need to get a bit more tricky. We need to simplify this. We can write that's the square root of 8 times 10. No, actually, if I rub that out, 8 times 10 to the 6. And it's over the square root of 100, which is 10. And 8 is 2 root 2. The square root of 8 is 2 root 2. And the square root of 10 to the 6 is 10 to the 3. And that's over 10. So that then becomes, cancel, cancel. So that becomes 2 root 2 times 100. Which is 200 root 2. Now that's quite a lot of working, and the more working you do, the more mistakes or the more opportunity you have for making a mistake. So what you can do is, if you've got a sine curve, now this only works for a sine curve, everything else you're going to have to do the working, but for a sine curve, the RMS is always going to be the amplitude over root 2, provided it's for a full cycle. Now I knew that. That was why right at the start I did a little sketch to see where this 1 over 100th came, and I could see now that I've got a full cycle. So I'm finding the RMS over a full cycle, so I can simply say my amplitude was 400 over root 2, which I can rewrite as, what can I write that as? I can rationalise the denominator. I can say that that's equal to 400 root 2 over root 2 times root 2, which is 400 root 2 over 2, which is, as before, 200 root 2. So doing it that way, if it's a sine curve and it's for a full cycle, doing it this way saves you an awful lot of time and gets full marks. As does doing it this way, but it is a lot quicker to just say, if it's a sine curve and we're finding the RMS over the whole cycle, then my RMS is just going to be the amplitude over root 2. Now I said at the start of this video that all we're doing is actually just using integration now. There's no new techniques. We're just putting integration into various formulas. Now again, I'm not sure if that's the right page number, but there is a discussion on this in the textbooks, and we can just use integration to find the length of an arc of a curve between a couple of parameters. So it's just a formula. It's a formula using integration. Now I will do the second one in class, but I'll do the first one here. We're given, find the length of the curve y squared equals x cubed between x equals 0 and x equals 4. Now we've just got a little bit of a difficulty here. We actually need the derivative of y squared, and we've been given y squared, so what we need to do to start off with is we need to find what y is, so then we can find the derivative and square that. So let's find dy by dx. Dy by dx is going to be 3 over 2 x to the power of 1 over 2. So then the bit under the square root sign, so then we've got 1 over the derivative squared. Now it's not the second derivative, it's the actual derivative squared. So it's going to be 1 plus 3 over 2 x to the half squared, which would be 3 over 2 squared is 9 over 4. X to the half squared is just x. So now we've got what we need to integrate. So now the arc length is going to be the integral between 0 and 4, as per the question, of the square root of, or to the power of half of, 1 plus 9/4 x. So integrating this by substitution, which you might need to go back to topic 10 to look at, is going to give us 2/3 times 4/9 times 1 plus 9x/4 to the power of 3/2. Whoops, sorry, that should have been a half. I forgot my half there. That should have been the square root of that. So this is now 3/2, and we're going to find that between 4 and 0. So doing the arithmetic, it's 8/27, and that would be 10√10 minus 1. So it's approximately equal to 9.07. Now, we don't have a unit, but we'll just call it units. And that is the arc length along the curve that's expressed as y squared equals x cubed between x equals 0 and x equals 4. We will do this in class, but just to set the scene, what we're looking at here is corrugated iron. Corrugated iron is used extensively throughout the world as a building material, and you will know better than I that bending the material into a regular wave pattern gives it greater strength than if you're using a flat sheet. Another example of a light, thin, weak sheet that's flat, that's made much stronger by having regular folds put into it, is corrugated cardboard, which we use for packing things, protecting goods in transit. But to make corrugated iron, you need to bend a wide flat sheet into waves, and the resulting corrugated sheet is then narrower, of course, or as my children would say, obviously. So what we've got here is we've got a panel that has a finished width of 106.7 centimetres, and each wave has a period of 10.67 centimetres. That's the distance from the top of each wave to the top of the next wave, and it has amplitude of 1.35 centimetres. So that's the height from the midpoint of the wave to the top. And the question is, how wide should this have been to give us a corrugated sheet that's 106.7 centimetres wide? So we'll look at that in class, because it does require that we've figured out the actual sine curve that it is that we're working with. So we need the sine curve. And we'll look at that in class. This is another practical example where we're going to use the integration to find the arc length. So you're talking here about the cross-section of a parabolic dish, and you're given the fact that it is modelled by y equals 0.04 x squared, and you're asked to find the arc length from -5 through to where x is equal to 5. So we can just start off with y equals 0.04 x squared, and the derivative of that is going to be 0.08 x. Okay, the arc length doesn't matter whether you call it R or S, whatever, is going to be the integral between -5 and 5 of the square root of 1 plus 0.08 x squared dx. Now, probably in this case, you would have used something like Wolfram alpha or some other proprietary thing to say that the length is actually equal approximately to 10.2, and it's given you are given a unit, so make sure that that one has a unit as well. So the length of the supporting beam should have been 10.261, or the supporting band, sorry, should have been 10.261. For this question here, to find the length of the curve on a span of the central span of the Golden Gate Bridge in San Francisco, this is not a question you'd be expected to do in class from this amount of information. In order to do this question, you actually need to be given the equation of the span, and assuming it's a catenary, you'd have been given the equation. We will do this one in class where I will give you the equation. But once we have the equation, it's just a simple matter then of using the formula as before. Our problem becomes slightly more complicated where the curve is expressed parametrically. So I'll do the first one and we'll do the second one in class. So for the first one, we need to find the length of the curve where x is 2 cos cubed theta and y equals 2 sine cubed theta. All it is a matter of is finding the bits and then putting them into the rule. So we can find dx by d theta. Dx by d theta is going to be 6 cos squared theta times negative sine theta, so we can tidy that up and write it as -6 cos squared theta sine theta. We also need to find dy by d theta, which would be, so y is 2 sine cubed theta, so the derivative of that would be 3 times 2, which is 6 sine squared theta times the derivative of sine, which is cos. I'm just using the chain rule there for both of those. Now, excuse me, I need to find the square of each of those derivatives and add them. So let's just do that. So dx by d theta squared plus dy by d theta squared. So that would be the square of the first one. So that would be 36 cos 4 theta sine squared theta plus 36 sine to the 4 theta cos squared theta, which, if I take out a common factor of 36 and take out a common factor of sine squared theta cos squared theta, what I've got left is cos squared theta plus sine squared theta. And of course, cos squared theta plus sine squared theta is conveniently 1. So we're left with 36 sine squared theta cos squared theta. So now, putting this into the formula that we've got here, so now the arc length is going to be equal to the integral between 0 and pi by 2 of the square root of what we've just found, d theta, which means what we're doing is we are integrating 6 sine theta cos theta between 0 and pi by 2, which we could rewrite using a trig identity as the integral between pi over 2 and 0 of 3 sine 2 theta. Just using a trig identity. Look it up if you can't recall. So that now makes it very easy. We can put the 3 outside and we can integrate sine 2 theta to give us negative cos 2 theta over 2 between pi by 2 and 0, which gives us 3 times a half minus negative a half, which is 3 times 1, which is 3. So, pretty straightforward. We needed to find dx, we needed to find dy, both of them with respect to t. We needed to square both of those, well, in this case with respect to theta, find the square root of it, play around with some trig identities, integrate it, put in the limits, and we're done. I will do the second one in class. We can go further and again just use integration in a formula to find the length of a spiral, and in this case the spirals, it's where the spiral's done 2 revolutions, so it starts at the origin, goes round and comes back to here. So if we have an example of a function where we're already given the function here, then we can find the arc length as it goes right round. Okay, so what we've got is we've got that r is equal to 1.618013 e to the power of 30635 theta. Now we need to find r squared. So we can do that. That would be 2.61797 e, and double that to the power of 6127 theta. And for the formula we also need to find dr by d theta, which would be 0.49568 e to the 0.30635 theta. And we need to find that squared. All we're doing is we're just finding the bits for the formula. So that then becomes 0.24567 e to the power of 0.6127 theta. Okay, so now we've got all the bits. We just have to put it into the formula. L is equal to the integral between 0 and 4 pi, because that's what it takes to go round twice, of the square root of r squared, which was 2.61797 97e to the power of 0.6127 theta plus dr by d theta squared Now, that's too much for this course. You would probably be expected to do this in Maths 2 for the degree, but otherwise you just use Wolfram Alpha or something else, and we can get that it's approximately equal to 254, and depending on the units, I'll just put units. But you can see the potential of integration. So many formulas. You know the techniques of integration. It's just a matter of following the formula and putting the bits in. Painting by numbers, really. Another example is finding the length of a spring that's in the shape of a spiral. It's got 7.5 turns, where the inner radius is 5 millimeters and the outer radius is 15.5 millimeters. You wouldn't be expected to do this, but once you've got the formula, it's not hard. Once you've got the formula that r is equal to 5 plus 0.22282 theta, and then the derivative of that, that's quite easy to find. Oops. And your start angle is 0, and after 7.5 turns, then it's going to go through 7.5 times a turn would be 2 pi, so 7.5 times 2 pi, which would be 15 pi. All you need to do to find the length of it would be to find the integral between 0 and 15 pi of the square root of r squared, which we've got r, plus the derivative squared with respect to theta. Again, it's a bit beyond the course, but you need to see what this sort of thing can do. So that's 483.1. Again, you'd use Wolfram Alpha, and I think we're working in millimeters, so the spring itself would be 483.1 millimeters would be the spring length.